Hi everyone, this is Bradley Bush with another algebra video. Today we're talking about modeling exponential growth and decay, and here is our to-do list. We have, first of all, we'll talk briefly about the model, a growth model or a decay model that's exponential. Then second, we'll talk about what the parts of the model are. So the first item on the to-do list is more of a model definition, and then we'll break it down in step 2 and say, well, what does this part mean? What does this part mean? So hopefully by the end, you will completely understand each part of the growth or decay model that you would see in algebra. And then the last step will be a graph. We'll discuss what the graphs look like for both a growth and a decay. All right, let's start. So here's the model. What we're dealing with really is something that looks similar to the left, f of t equals a naught e to the kt, or here on the right, a equals a naught e to the kt. Either of them are okay. The left one just uses the function notation with f, and the right one just uses a instead of, or you could think of it as y. Either one is okay. So let's break down the different parts. So first of all, let's talk about the initial amount. So a growth and decay model discusses growth of something, right? Most often it's some type of a population, like a virus, for example, or it could be the US population. It could be a population of rabbits. It could be the decay. If you're talking about a decay model, it could be radioactive decay, or it could be decay of carbon-14. That's a classic example. There are a lot of decay and growth models that can be very well described by this simple model here. So there's always a time 0 when you start a model, and then you want to see how it grows moving forward in time. So at time 0, we want to know what the initial amount is. So initial amount, you can think of the a in amount as the quantity we're looking for, because the initial amount is a naught here on the left, or a naught here on the right. Now, when I say a naught, that's a with a 0 as a subscript. That's pronounced a naught. So that's the beginning. So if you have the start of your time population, say you're growing bacteria, and at the start of your experiment at time equals 0, you have 20 bacteria that you've placed in a petri dish. So a naught would be 20. That's your initial amount, your initial population amount. So we have a growth or a decay constant. So because your model either grows or decays according to some constant, and that constant is the k you see on the right model, and also the k you see on the left model. So the k is the growth or decay constant, and it is a growth constant if k is positive. It's a decay constant if k is negative. So if you see a model that has a negative constant in the exponent, and you know that it's an exponential model of growth or decay, then that k, if it's negative, you know that it's a decay model. If that k is positive, you know that it's a growth model. Super simple. So our model starts at time t equals 0. I should probably put that as well over here. Initial amount at time t equals 0. Initial amount at time t equals 0. We have, so at t equals 0, we've got initial amount of, say, 20 bacteria in your petri dish, and we let the timer go, and all of a sudden time is moving forward or to the right on the x or t axis. On the horizontal axis, time is moving forward, and the population's growing if it's a growth model, or it's decaying if it's a decay model. So at any specific time, say time 2 hours after we let the experiment grow, there's going to be a specific population number at that time. So it's not our initial population. It's either grown or it has decayed, or it's gotten bigger or smaller. So that current amount at any time t, we have to have something that describes that, right? So we have the current amount at any time t, and that is the a here, or the f of t here. What else do we have? Time, our variable. We've got to put it, we have to have a variable, right? In a model, you always have a variable. Oftentimes in algebra, it's x, but here it's t for time because that just sounds more appropriate. But you could just as well do x. So variable, we have a variable in this model. Variable time t. And that's the purple. That's the t that is now circled in purple in both places. You also see it right here on the left as the independent variable. So you know that t is the variable because it's what will be put in. So you could say, well, what's the population at t equals 5? And 5 would go in right there. So what else do we have left? Oh, we've got one last thing. We haven't talked about this e. Well, what is that e? That e is the natural exponential. E to the x. And if you're wondering, e is somewhere about 2.718, so on, so on, and so on. So that's what the e is. And we're almost done. Almost done. We need to give you some definitions, though. A naught, A, and K. So A naught is the population at time 0. A is the population at any time after 0. And K is your population growth or decay constant. Those are all real numbers. So if you're wondering what this means here, this little e, that means element of, or belongs to the set of. So A, not A and K, belong to the set of real numbers. That's what this R is, with a thick left side. The real numbers. That's just mathematical shorthand for all real numbers. So A naught, A, and K, those are real numbers. I mean, they can be anything as long as it's a real number. So no imaginaries. And what else do we have? Time, Generally speaking, time starts at 0 when the population begins to grow or decay, and then moves forward until people are no longer interested in watching it grow or decay, and then it stops. And one last thing, k, which is the growth constant, cannot be equal to 1, because then there wouldn't be any growth or decay. The population would stay constant. So I think we've covered it. That's the model. You know all the pieces now, and let's look at a quick graph. On the left-hand side, we have a graph of the exponential growth. We know it's growth, one reason, because the k constant, the growth or decay constant, is positive, so that means we know we're growing. We have an initial value of a naught. You can see a naught on the left, on the vertical axis, and there's an actual spot on the vertical axis where a naught exists. So that would be, say, we're going back to our Petri dish example, and we have 20 bacteria to start with. That would be 20, right? Here you'd have 20 bacteria starting. And then as time progressed forward, whether that's days, months, however you are counting your time, say we're doing it in days, then as time moved forward, your population would grow. So as you go to the right, you're going up on the graph. If you have a decay constant, then over on the left, we have our decay. We have our a naught. So we have a specific value for a. So say we're watching the amount of radioactive decay at a bomb site, and they have quantified it. They've measured it, and they say, this is how much radioactive material you have. And say it's, I don't know, it's a lot. I don't know how to quantify radioactive decay, so I won't even try. But this would be the number. 1,000 pounds, whatever it might be. I don't know the best way to quantify it. But there's a number there that tells you how much is present. And then as time starts ticking, we have, we'll do this in maybe years. As time moves forward, the amount of radioactive decay decreases. So it goes down as you move to the right. The graph moves or drops as you move to the right. We also know this is the decay because the k value is going to be a negative value. And that's about it. Hopefully you guys feel a little more comfortable now with exponential growth or decay models. You know all of the parts, and you know what the graphs look like. If you have questions, let me know. Have fun modeling.